Okay, welcome back to Feedback Control Systems. This is Module 8.2, Introduction to Root Locus. The objectives of today's module are to define the root locus, discuss properties of the root locus, and finally do some sketching of the root locus. So first of all, we're going to define the root locus by starting with an example. And the example we're showing here is what we're going to call an auto-tracking example. So for the input, we're going to have a subject, or in this case, you could think of it as a person. It could be an object, could be whatever. That's some sort of reference input that we have. There might be some sensors and amplifiers and cameras that are following the subject, etc. So you could think of this as some sort of surveillance or tracking system. And what we want to do in order to track the subject is we want to make sure the camera position is being moved. You can think of that as the output of interest. When we look at the system, we could formulate a closed-loop transfer function as shown there, given our input R, our output C. We've done this in previous lectures, so I'll leave it to you to derive that closed-loop transfer function. And in this case, we can see that there's a gain K that could be the product of an amplifier, K1, and some gain relative to the motor and camera, K2. So that'll be the product. We'll just call that K. Now, as we vary K, we could look at the pole locations. And again, the pole locations would be in the denominator. Set the denominator equal to 0. We have a second-order system, so we could solve a variety of ways, quadratic formula or other. And what we do is, what we're showing up here is as we vary K from, say, 0 to 50 in 5-unit increments here, we're going to have two poles, and we're just going to map what those two locations are. Okay? And we'll see as we go through this, just looking at the two pole locations, based on previous modules, we said when there are two poles both on the real axis, we call that an overdamped case, as highlighted there in blue. When the poles are equal in both on the real axis, we call that a critically damped case. And then finally in green here, as we continue to increase the gain, what we're going to see are the pole locations are going to become complex conjugates of each other, go off axis, and therefore we're going to call that an underdamped case. And in that case, we're going to see some sort of overshoot and then some oscillatory behavior before that response dies down. So we can plot that table in a pole plot map on our S-plane here. We have our real axis and imaginary axis. Here's the imaginary, here's the real axis here. And so for each of those gains, starting from K equals 0 all the way through 50, we can see the poles start both on the real axis. As we increase the gain, the poles come together, both hit -5, and then they go off axis and go away as complex conjugates. And so looking at that pole plot table, we're going to introduce a plot just to the right of that will look very similar, and we're going to call that the root locus. So as we vary this gain K from 0 and above, again, we're just kind of showing what's happening. The two poles kind of merge, come together, merge, and then go off axis. And instead of showing all of the x's per se, we're going to just start with the pole locations where K equals 0, as shown here. And then with the arrows, you can see they're merging, coming together, and then eventually going away from each other. So that definition, instead of, again, plotting all those x's, we're just going to show that as a root locus plot. And it will give us some insight as we vary that gain parameter K, what system response, and again, the pole locations that we have. So again, that system response could be overdamped or critically damped or underdamped, etc. Now, some of the properties of the root locus we want to discuss next is here we have a goal, which we want to allow a quick root locus sketch for higher order systems. So what we saw there was a second order system. Not everything in life will be second order. We might have third, fourth, fifth, even higher order systems. So our goal is to teach you some of the principles here of allowing you to quickly sketch that root locus. And so first we're going to come along and introduce a general closed loop transfer function, T of S, as we're showing here. And we've seen this before. So given that general closed loop transfer function, we can find the poles, as we did in the previous example, by setting the denominator equal to 0. And so when we do that, setting this term equal to 0, notice what we can do. We can bring the 1 to the other side here, and that's what you see here. We're going to say kgh equals -1. After setting that to 0, let's move the 1 to the other side, and that'll become a -1. And as we do that, what we're going to see when we say -1, what does that mean sort of physically here? We could say that's a magnitude of 1, but we could say the angle is 180 degrees. So for example, if we were to draw a sine wave, you can imagine a sine wave, we would say what's the negative of that sine wave? Well, that would go the opposite. So the negative of the sine wave would be opposite of that. So you could say that sine wave is 180 degrees out of phase, and that's the notation that we're showing here. As you see k vary here, what you'll see is this term always here will represent an odd number, and what we'll get is again a factor of 180 degrees. Okay. An alternative view of this is we could first look at the magnitude and say, again, if the magnitude of k times g times h equals 1, certainly we know that the angle here is going to be as shown here. And so we can basically just focus on that magnitude characteristic. And so now we can rewrite that characteristic as a way and solve for k, the gain k. Because we already know that the angle is going to be this odd multiple of 180 degrees. So we are left with solving for the gain k as 1 over the magnitude of g times the magnitude of h. Continuing to look at the properties of the root locus with another example here. So we have our transfer characteristic, our open loop transfer characteristic as shown there. And you can see the poles and zeros, again the poles in the denominator, -1, -2. You can see that directly from here. And then again the zeros in the numerator at -3 and -4. So we can plot those first on our S-plane. And as we look at that open loop transfer function, we could put it in that form. For example, kgh. Now, because we have a unity feedback system here, we'll just say h is 1. And so we'll have the gain k, and then all of the other things, as we've already mapped on the S-plane, represents, you could think of it as g of s, the open loop transfer function. Now, to get a closed loop transfer function, again, we've showed you this in previous modules. I'll leave that to you as an exercise. Hopefully, you should be very good at this by now, creating this closed loop transfer characteristic as shown here. And now what we could do is we could, I will say, randomly evaluate test points in the S-plane to see if it could possibly be a closed loop pole. So if you remember, we started with the second order system, and as we varied k, those two poles came together, met, and then went off axis. And so if we did a test point that fell anywhere on there, and if it satisfies this criteria, then we'd say, yes, it's a closed loop pole. However, if we did that and the pole was way over here, notice that as we vary the gain k, we would never get that, so that would not be a closed loop pole. So here is a method we could do to evaluate if that test point would be a closed loop pole or not. So the test point that we're testing here is -2 plus j3. You can see that point plotted here, as well as the open loop poles and zeros. Now notice what we have here is we have all of the different angles and the various lengths, L1, L2, L3, L4. And so what we know are all of those angles have to come together and be an odd multiple of 180 degrees. So as we look at this, we're going to notice the following, which is theta 1, theta 2. Notice they have positive signs. And where are theta 1 and theta 2? They're here. They are the zeros. So the zeros will have a positive angle associated with it. And then we have the negative theta 3 and theta 4, which are our poles. So our poles, so we basically have our zero angles minus our pole angles. And if those two come together and form an odd multiple of 180 degrees, that's one way we could test to see if that test point is indeed possible to be a closed loop pole. In this case, I will leave it to you based on geometry. We looked at this, I believe, in Module 8.1, where we looked at the vector characterization of these poles, how to calculate these angles and these lengths. And so we'll leave that again to you as an exercise. But what you'll see is when we finally combine them, that the net effect is negative 70.55. So clearly this is not an odd multiple of 180 degrees, so therefore that point is not on the root locus and therefore cannot be a closed loop pole. We can try another point. So this point here is not shown on the graph. You could certainly sketch it. Find your negative 2 and then your j term root 2 over 2. It would be a little lower than what we're showing here. I'll just randomly draw it somewhere down there. So now we could test, is this point on the root locus? And if so, we could find the value of gain to get it. So I did not show you the angle calculation. I'll leave that again for you as an exercise given our example here. And what you'll find is that will be an odd multiple of 180 degrees, so it indeed will be on the root locus. So now what we're going to do is use this criteria here based on the magnitudes and actually find the gain, the value of k, where that point will exist on the root locus. And what we'll see here from this criteria is the value of k is going to be the product of the lengths of the poles. So poles right here in x's, that would be L3 and L4. We can find those two lengths. Then we divide that by the product of the zero lengths. That would be our L1 and L2 terms. So I've listed here L1 through 4 as shown. I'll, again, leave it to you based on the previous module to come up with those. So between the worked examples that we've shown and the previous modules, you should really get to the point of being able to calculate these. So again, I'm not going to go step by step, but again, just give those to you and solve for the value of k here. You'll see that that's roughly a third, 0.33 as the value of gain that we could put here in our transfer characteristic such that when we draw the root locus, as we look at the root locus based on this open loop criteria here, that these two poles would come together and then go off axis here, and then there would be this point right here at negative 2 plus square root of 2 over 2 that would be on the root locus, again at that gain of k equals 0.33. Now we're going to further explore the sketching of the root locus. And first we're going to start with some definitions. So first we're going to define a branch. What is a branch? Now this is a path that a pole will travel, and it's going to be, it's equal to the number of closed loop poles. And so we'll see this a little bit more as we go through. Now, symmetry, physically realizable systems. So systems we can build, not sort of theoretical exercises, but systems we can build don't have complex coefficients in their transfer functions. So the root locus is going to tend to be symmetrical about the real axis, meaning we have these complex conjugate poles here, and so that's going to be a benefit to us as we go forward. Next, we'll look at real axis segments, and real axis segments are the following. So on the real axis, as k is greater than 0, so as we increase the value of gain, the root locus will exist to the left, and this is important, to the left of an odd number of real axis finite open loop zeros. Okay? So as we look at this, let's assume we have a variety of test points here along the real axis, and so p sub I. So we have P1, we have P2, P3, and P4. So for this test point P1, you'll see a variety of poles and zeros here, and so as we look through this, what we'll find is that the root locus will exist to the left, okay, to the left of an odd number of real axis finite open loop zeros. So here is a finite open loop zeros, so certainly this point would be a point on the real axis that would exist. More on that, again, as we work some examples. These definitions, we'll just kind of present these definitions, and we'll go back and forth with them as we work examples to try to bring these definitions and criteria to life. Okay. Next, we're going to see starting and ending points. And so what we'll find is, based on our closed loop transfer function T of S, it can eventually sort of, in the limits of k being very small, you could think of k approaching 0 here, which is shown on the left. So you can think of small k as k approaches 0 here. The root locus begins at the finite and infinite poles of GS HS. And so where does that take us here? If we look at the denominator here, at the finite poles, set that equal to 0 for small values of k, what we'll see here is that this denominator, the root locus is going to essentially start there. And the root locus, and again, you can think about that when we started with the k of 0 case for the second order system, right? We had k of 0, it started at the two poles, it went, and then it sort of went off axis from there as k got bigger and bigger. And so as k approaches infinity, what we'll see in the closed loop transfer characteristic is that the root locus ends at the finite and infinite zeros of GSHS. And so notice here, in the denominator of the closed loop transfer characteristic, with large values of k, notice we have n, g, and h. That is the numerator of gh. Those were the zeros of that characteristic. So that's what we'll see is notice that closed loop transfer characteristic, as k is very small, everything starts at the poles, and then as k gets much, much bigger, sort of in the limit as it goes to infinity, that root locus goes from the poles to the zeros. Okay, so that's going to be a very important part as we're drawing the root locus. And then the next characteristic is the behavior at infinity. So the root locus approaches straight lines as asymptotes as the root locus approaches infinity with the real axis intercept, sigma sub a, and the angle at theta sub a. And so sigma sub a, this is the real axis intercept here. You can see it's going to be the sum of the finite poles minus the sum of the finite zeros divided by the total number of poles minus the total number of zeros. So the definition, the example we're going to work on the next slide, will bring this, I think, to a little bit more life in instinct for you. And the angle here that those asymptotes approach, you can see the definition there. The denominator is the same as we had for sigma here. The numerator is what differs, and you'll see that again as we work the example on the next slide. So again, these are sort of the high-level definitions. My experience is a lot of times students struggle with the definitions. However, stick with these definitions. You could have this slide sort of printed on the side, and then as we work examples, you'll see these definitions sort of come to life. So on this slide, what we'll see is that example. So we have the two definitions from the previous slide shown there in terms of those asymptotes. And for this system here, we can start by first looking at the real axis intercept here, sigma sub a. So the first thing we could do is based on this open loop characteristic. Notice we have a 0 at -3, and then we have the poles down here. And the poles, we have a pole at 0, -1, -2, and -4 that we can see directly by setting that denominator equal to 0. So there are our poles and zeros of our open loop characteristic. Now, based on the definition of sigma sub a, what we're going to do is sum the finite poles. So the finite poles, we have 0, we have -1, -2, and -4. Okay, we're going to sum those all together. And then what we're going to do is subtract from that the finite zeros. Well, there's only one 0 that's located at -3. So as we work that out, the numerator term comes out to be a -4. Okay, and then what we'll see in the denominator is how many total finite poles are there? Well, we have a total of 4 poles. Just looking at this map, we have 1, we have 2, we have 3, we have 4 total poles, and we have 1 0. So 4 minus 1 is going to be 3, and then that's what you'll see in our real axis intercept. Those asymptotes will kind of merge and hit -4/3. And so that is going to be an asymptote as we are going to, it's going to help guide our root locus as we vary k. Let me get rid of some of the ink here just to make the slide a little bit clearer. And there's our -4/3 point here. Okay. Now, the next thing we are interested in is this angle here. What is the angle of those two asymptotes that go? And this is our definition. And so we're going to vary k here. Notice the denominator is the same as the previous one here. So 4 minus 1, so this denominator right here, 4 minus 1 is going to be 3, and then this numerator term here is going to be the same. So it's going to be, as we vary k, something over 3. And so first we're going to say, hey, for k equals 0, substitute in 0 here, we're just going to be left with pi, so pi over 3. Okay, so that would be this angle right here, pi over 3. I believe that's 60 degrees. And so that would be the first angle, that asymptote. And then what we'll see for the k equals 1, if we substitute k equals 1 right there, we're going to get k equals 1, we're going to get 3 pi in the numerator, so the 3's cancel, and I'm left with just pi. Okay, so relative to that asymptote, I have 60 degrees, and then I have 180 degrees, which would be sort of that direction right there in terms of an asymptote. And then finally, when I substitute k equals 2, I'm going to get a 5 pi over 3, which would be this angle right there. So relative to that point, that intercept point, -4/3, I have two asymptotes, basically 60 degrees and then minus 60 degrees that I have there. And then I have this 180 degrees. And what that's going to do is help guide essentially where these poles go. So as I look, these two poles right here, okay, as I increase gain, those two poles, the one at 0 and -1, they're going to come together. But instead of going straight up, they have to asymptotically approach those lines that we found here. And so that's what you'll see is this curvature, the curvature of the root locus, and eventually they'll asymptotically approach that, and they're going off to the zeros at infinity. So you'll see this starting and ending point term down here is the root locus begins at the finite and infinite poles. So for example, 0, -1, very low values of k, that's where they're starting. And then as we increase k, they come together, meet, and then they go off axis, but those asymptotes are guiding them away, so they're not going to go straight up, they're guiding them away. And what they're going to do is they're going to approach finite and infinite zeros. So these two right here, you can see, as we're going off axis, these are approaching zeros at infinity. However, this pole right here is approaching a finite zero. That -2, as that gain increases, that -2 pole is marching closer and closer to that zero. And sort of those two, in essence, will kind of cancel each other as k gets big enough. -2, -3 have that effect of essentially wiping each other out. And look at this last pole right here, that asymptote -4. Where does that go? That just goes off to infinity that way. And so really the dynamics of this system will be governed by wherever these two poles, and let's erase some ink here. Okay. So this one essentially will come out of play. These two essentially will cancel. And then again, basically, these two poles will dominate the system here. And for example, if we want a certain damping, right, this is our damping ratio, we would select a value of k for example, right about there, and that would dictate our response. So even though we had 4 poles, we can, in sort of the limit here, approximate this as a second order transfer characteristic because of what I had mentioned to you sort of before. And so what really helps us as we're sketching this higher order system is we are looking at these asymptote angles here, and the point along the real axis, sigma sub a, and then the angle theta sub a, that really helps guide us in our analysis of the root locus. So that will conclude this opening module on introducing root locus. In upcoming modules, we'll dig in a little bit deeper, work some more examples, and then we'll see how we can use this for designing systems with desired transient responses and other. If you have any questions on any of this material, please don't hesitate to reach out. Thank you.